There's the attendance form. Let me grab a couple things here before we get going. One second. Sure. All right, sorry. Let's just look at some stuff. Volume's on. There's the attendance one more time. What do you guys want to talk about? I mean, there's obviously lots of stuff to talk about, but anything specifically come to mind before I just start blabbering away here?
I'm not sure if you watched Professor Rodriguez's lecture, but we just finally covered a little bit of what finding the eigenvectors and their role to their role for system of differential equations. We haven't covered. We ended off with the flowchart saying like talking about the spiral of the nodes and the saddle point. That's just about it.
Okay. And I'm assuming, looking at Rodriguez's, sorry, not Rodriguez, Rademacher's notes, he's starting to talk about nonlinear stuff, it looks like. Which looks kind of crazy. So I feel like to continue doing some examples, I've got a couple examples I want to do. Because I think we should still talk about like graphing the phase plane and kind of seeing what's happening there. And again, I think it's really worth our time to use the tools available to us. I'm going to definitely get p-plane up here so I can use it when I want to. Let's kind of look at, we'll do some nonlinear, I think, today, but let's start with a couple linear examples. I know the linear examples aren't particularly exciting, but they are useful. So let me see here, 1 second. Let me grab this, let me do that, okay. I like my board's getting closer and closer to me. Pens, where'd you go, pens? Okay, so yeah. So today we have this system of differential equations. And we'll do the whole, I thought I just grabbed a good, oh no, I didn't. I was lying to myself. I thought I had a new black pen. It's not a new black pen, it's an old black pen. There's a new blue pen. I'm gonna have to go to campus soon and steal some pens because I'm on my last box of pens. So let's say we have this system. The xdt is -2x plus y. And dy dt is 2x minus 3y. And maybe we'll look at some initial conditions in a minute. That's not super important, but we can just pretend for now. We can say, like, let's say we have x of 0 equals 1, y of 0 equals. I want to make sure I'm not on one of the eigenvectors. Let's say -3, just for fun. Okay, so let's do the whole thing. Let's find the general solution to this, all that. So let's see here. So I know my matrix looks like this. I'm going to find the eigenvalues. And now, just for fun, to show you a different way, I'm going to remind you that there is another way you can find the eigenvalues. You can find the eigenvalues as tau plus or minus the square root of tau squared minus 4 delta. Yeah, over 2. Where again, tau is the trace, which in this matrix is -2 plus -3. The trace is always the sum of the diagonals. So it's -5. And the delta is the determinant here. So the determinant is 6 minus 2. So my eigenvalues are -5 plus or minus the square root of -5 squared minus 4 times 4 all over 2, which is -5 plus or minus the square root of 9 over 2. -5 plus 3 is -2 over 2 is -1. -5 minus 3 is -8 over 2 is -4. Yeah, that's right. So that's one way you could find the eigenvalues if you were inclined to do so. Totally not necessary, but we could. Or you could do it the other way. In fact, let's do it the other way just to make sure that this is right? Just so we can see for real this works as well. So we did it the other way. We have the determinant of -2 minus lambda, 1, 2, -3 minus lambda. And we get these multiplied together. I'm just going to multiply it out. This times this is going to give me lambda squared plus 3 lambda plus 2 lambda is plus 5 lambda plus 6 minus 2. So you get lambda squared plus 5 lambda plus 4 equals 0. And then definitely factors as lambda plus 1 times lambda plus 4, which gives us -1 and -4 as our eigenvalues. So great, it works. So you can totally use this if you want. It's kind of neat, but it's not super necessary. So now let's find the eigenvectors. Cool, let's hit myself in the face. Okay. So we have the matrix. What do we got here? -2, 1, 2, 3. And for lambda equal to -1. So actually, before we even go any further, right? If we were just being asked to talk about the stability of our equilibrium, we would say, oh, 0, 0 is our equilibrium, and it's definitely a stable node, right? It's a sink because both my eigenvalues are negative. So if we were doing that, we could stop here. We wouldn't have to do anything else. But we want to do more because we want to kind of just see the whole thing. So if I got lambda equal to -1, sorry, we got, let's see, a so -2, 1, 2, -3 times v1, v2 equals -1, v1, v2. We just use the first equation, so this times this is this times that. So -2 v1 plus v2 equals -v1. So let's see, adding to v1 and get v2 equals v1. So it looks like the eigenvalue for this one is 1, 1. Right? Let v1 equal 1 and v2 is 1. For lambda equal to -4, same sort of deal. Do this times the eigenvector is -4 times the eigenvector. So using the first equation again, I get negative 2v1 plus v2 equals negative 4v1. Add this, so I get v2 equals negative 4 plus 2 is negative 2. Let v1 equal 1, then v2 is going to be negative 2. So my eigenvector here is 1, negative 2. Okay. So now I'm going to draw a bunch of stuff. And I do think it's worth, so of course we could totally graph this on like, should I use Desmos? No, I should use Desmos. So let's go ahead and graph a bunch of things. Yeah, so I'm going to erase like everything except for the original matrix. So, I don't want to graph the stuff yet. I kind of do. I'm going to graph the stuff and then we'll go back and we'll find the general solution. So I'm going to graph a few things and then we'll come back. So I kind of want to try and graph this pretty well. Okay, so I'm going to graph 4 things to start. I'm going to graph the eigenvectors. So my eigenvectors, so for lambda 1 equal to negative 1, we had v1 equal to 1, 1. And for lambda 2 equal to negative 4, we had v2 equal to 1, negative 2. And so I'm going to draw the eigen lines. So the lines that the eigenvectors would go through. So if I go over 1, up 1, right? So there's the eigenline for v1. And now I should actually really be drawing it with the arrows going in, right? Because we know since the eigenvalue is negative, we're going to be pointing inwards. And it's almost dead. And then we also have v2 is over 1 down 2. Over 1 down 2. So, and then over 1 up 2. And again, sorry, it's hard not to just want to draw like a line, right? But again, we should be pointing in because the eigenvalues are negative. Okay. But I also, so these are the eigen lines, is what they're usually called. I also want to draw the, what are they called? The, holy smokes, the isoclines. So the isoclines, let's put it down here. Iso or null lines. Just a fancy word for where each partial derivative is, or sorry, where each differential equation is equal to 0. So if I do dx dt equal to 0, I get y equal to 2x. So I'm going to draw that one in blue. Let's do it in red. Red. So that's going to be, so y equals 2x. Take this line. And so this is the line where all the arrows are going to be either up or down. And that's because dx dt is equal to 0. We're about that in a minute. It looks like they're all going to be down, right? It would be weird for them to be pointing up here because they should be pointing inwards. So I'm guessing we're going to be like this. And similarly here, we should be pointing upwards. And then for the other one, let's do it in green. Here's the attendance form again. So for dy dt, which is 2x minus 3y equal to 0, we're going to get 2x equal to 3y. We're going to get y equal to 2/3 x. So y equals 2/3 x. So my rise over run is 2 over 3, so I'm going to go over 3 up 2. So in green, I have my y all isocline. And in red, I have my x isocline. And so for the y isocline, that's where dy dt is equal to 0. That means there's no change in the y direction. So along this, all of my arrows should be horizontal. And so a couple things to notice here, right? If you start at a point on an eigenvector, or I should say on an eigenline, you're always going to end up just going along that eigenline. Right? If I start here, I'm exactly just going to travel in this direction. If I start here, I'm exactly going to travel in that direction. Same for this one. If I start here, there. But if I start somewhere that's not on one of the eigenlines, like for example, if I started at the point 1, -3, which is down here. So what's going to happen is I'm going to get pushed, as the way I kind of like see it, by both of these eigenvectors, right? Like, so I'm going to kind of, and so what we really actually do is we say, okay, x is 1 and y is -3, and then we plug those into these differential equations. So, okay, if x is 1 and y is -3, then at this point here, dx dt is, let's see, -2 minus 3 is -5, and dy dt is, let's see, 2 plus 9 is 11. So we're going left 5 and up 11. So it's almost the slope of -2, because your rise over your run is 11 over -5, which is -2.2. So it's a little bit, right? This is a slope of -2, so it's actually a little bit steeper. So we're kind of going like that. So we're pointing in towards the origin. And so we could do that for a bunch of different things, right? We could plot a bunch of different initial conditions to kind of see what this looks like. But we can also tell that, and sorry, this is where I have to make sure I'm doing right. These null lines separate things, right? So we know, like, in between these two null lines here, we have to be going right and up. In between these two null lines here, we have to be going up and left. In between these two null lines here, we have to be going down and left. In between these two here, we have to be going down and right. But there's no other choice. So it kind of helps us see what's happening. And I know this is kind of a very kind of basic example, right, where you just have all these straight lines. The next example, we'll try and make it a little bit more interesting. But I did say so let's go ahead and finish, just because I think it's worth at least doing one more time, finishing finding the general solution. So we're most of the way there. In fact, we're all the way there. We just have to write it out. So our general solution is, again, right, it's x, y, or x of t, y of t, if you prefer, equal to c1e to the lambda 1t v1 plus c2e to the lambda 2 t v2. Right. I would imagine you guys have probably just committed this to memory by now. It's come up a lot of times. And then I'm just going to put in everything we know. So we have xy equal to c1e to the lambda 1 is -1 t times v1, which was 1, 1, plus c2e to the -4 t times v2, which was, sorry, I forgot what v2 was, 1, -2. And then we could use the initial conditions to solve for C1 and C2 if we wanted to. So with our initial conditions, which were 1 and -3, that's going to equal C1 e to the 0 times 1, 1, plus C2 e to the 0 times 1, -2. We're going to end up with 1 equal to C1 plus C2, and -3 equal to C1 plus -2C2. And then you can solve this in whatever way you find most convenient. I would probably isolate C1 here. Well, I'd probably say negative this plus this. So if I do negative this plus this, negative 3 plus 1 is 4. Negative C1 plus C1 is no C1. And I can do math. 2C2 plus C2 is 3C2. So I end up with C2 equal to 4/3. And then I end up with, well, if C2 is 4/3, C1's got to be negative 1/3. And I would probably check this to be sure. I plug those numbers in here. Negative 2 times 4/3 is negative 8/3, plus negative 1/3 is negative 9/3, which is negative 3. So that checks out. So my particular solution looks like xy equals, I'm just writing this again with C1 and C2 plugged in. So it's negative 1/3 e to the negative t v1 plus 4/3 for C2 e to the negative 4t times 1 negative 2. And that would be our particular solution with these initial conditions. And we can also, so just to kind of go back to the graph for a second, we can totally look at the graph of this.
Do you have a question?
Yeah.
So when we were trying to solve for the particular solution, I understood how we got 1 equals C1 plus C2. How come T is 0 though? That's a problem.
Because the initial condition, it doesn't have to be, right? It can be any like initial condition, but we were given x of 0 equals 1 and y of 0 equals negative 3. But if someone else could give you a different initial condition where it was like x of 2 equals something and and y of 2 equals something, which would be worse because then, right, this wouldn't simplify quite so nicely. You'd have an e to the negative t or negative 2, which is still solvable. It just is less easy to do.
Thank you.
You're welcome, of course. And so if we look at let me share my screen here for a sec. So looking at the direction field for this, we hopefully see something very similar to what we're drawing here. So this definitely looks like it's a sink, and we can start. So in fact, let's go to our initial condition. So I go over to 1 for x and negative 3 for y. There's my initial condition, right? And so we see, okay, yeah, we are definitely starting there, but any initial condition is going to make us move towards the origin. It just, right, the closer we are to one of the Eigen lines, the more of a straight path we follow. And so if I actually start on an Eigen line, like over here at 1, negative 2, right, I'm just going to have a straight shot to the origin. Or over here at 1, 1, I didn't quite get it. Pretty close. Okay, whatever. Close to a straight shot to the origin. Let's see if I can get it right there. Yeah, okay. But if we're kind of in between the two Eigen lines, like say somewhere right here, we kind of have a more curved path, right? Because we're being pushed that. Oh, you guys can't. I'm like pointing at my screen. Like we're being pushed this way. You can totally see me. No, you can't see me pointing at my screen. But we're starting here, right? And we're getting pushed up, but we're also getting pushed over. So we're kind of moving, a little bit over, and then we're kind of right. The more we get closer to this Eigen line, the more vertical our path is. Sorry, isocline, not eigenline. Right. So yeah, that's what's kind of happening there. But I think we're ready to talk maybe about a non-linear example. Let's see if I've got. Sorry, my phone just started ringing. Yeah, here we go. Sure. That's a little bit more. Sorry, if I had an example ready to go here. 1 second. Sure. Yeah, all right, here's a more interesting example. Yeah, I think that's a good example. All right. So soon, I think, things are going to start maybe kind of, the pieces are going to start coming together, and we're going to start kind of talking about, what's the thing I'm thinking of? The linearization stuff that we were doing before. We're actually going to, maybe not going to use it super explicitly, but it is going to kind of play a role in how we talk about classifying other equilibria other than 0, 0. So yeah, I don't think this example is too terrible. So let's look at these non-linear differential equations. So here I have dx dt equal to 2x minus x squared minus 2xy, and dy dt equal to, I think it's the same but for y, yeah, 2y minus y squared minus 2xy. And I just want you to see, because this comes up relatively frequently, is that there's a symmetry here, right? This equation in x is just the same as this equation, but with x and y kind of interchanged. So when we start graphing stuff, I would expect there to be a lot of symmetry along the line y equals x. Like if you flipped it over the line y equals x, it probably look the same. So just something to keep in mind so that when you're graphing this, you're like, oh yeah, I can see what's happening here. So this is non-linear, right? It's not just stuff. So we don't just have a matrix, right? Where there's not, we can't do like A, B, C, D, whatever. So we're going to start looking at this one graphically and kind of forget about that stuff for a minute. So I want to look at the null lines. And I'll remind you, the null lines are just the places where either, what's our name for? Either of these derivatives is equal to 0. So I'm going to set this first one equal to 0. And let's see, I can factor out an x. X times 2 minus x minus 2 equal to 0. So I either get the null line x equal to 0, or I get the null line 2 minus x minus 2y equal to 0. And since I'm going to try and graph this, I'm going to solve for y. So I'm going to say negative 2y equals x minus 2. So y equals negative 1/2 x plus 1. So those are my null lines for x, right? So along those lines on my graph, I know that the direction of travel is going to be purely vertical because the dx dt part is going to be totally 0. Okay, and then we should expect the same sort of thing to happen for this, right? If I set this equal to 0, I'm factoring out a y. I'm going to solve for y. So I'm going to get either y equal to 0 here, or here I'm going to get 2 minus y minus 2x equal to 0. So 2 or negative 2x plus 2 equals y. So these are the null lines for dy dt, meaning along these two lines, all of my arrows are going to be pointing horizontally because the dy dt part is equal to 0. Okay. Sure. So this is when it becomes, I think, more important to really, really make sure you draw your null lines in different colors. Because here, the null lines being green and red, we see they intersect at one point, the origin, which was our only equilibrium. Now, let's do this. I've got a few things to draw. So let's use red and green. Sure, I'll go green over here. So we'll do the x null lines in green. and the y null finds in red. And just as a reminder for ourselves, we know that the x null finds are where dx dt is equal to 0, which means my arrows are going to be up or down, right? That has to be the case. In a similar way, the y null finds are where dy dt equals 0. So that means our arrows have to be pointing left or pointing right. Yeah, sorry, pen. Okay. So let's see. So my x null finds where'd you go? Over here, x equals 0, which is the vertical y-axis, and y equals -1/2 x plus 1. Okay, we grab one of my less good pen, green pens. So here's one of my y null finds, which is going to be kind of fun to drop. And then the other one was, I forgot what it was already. Y equals -1/2 x plus 1. So -1/2 x plus 1. So here's the 1. And then -1/2 x plus 1. Sorry, I'm having trouble thinking. So I'm going to have a y-intercept of 1 and an x-intercept of +2. So look like this. And along both of these lines, we know that our arrows are going to be vertical. We don't know if they're up or down yet because we haven't done any, we haven't plugged anything in yet, but we'll see that in a minute. Similarly, in fact, so we know by symmetry, right, that the y null finds, they were y equal to 0. And they were also y equal to, sorry, I forgot what it was, -2x plus 2. So it's got a y-intercept of 2, and an x-intercept of 1. That line is not quite as straight as I want it to be. Well, sure. Okay. And before we do anything else, here's what I want to say. I can look at this graph and see where all the equilibria are. There's an equilibrium here, where the different types of null finds cross. There's an equilibrium here, where the different types of null finds cross. There's one here, where the null finds cross, and there's one here, where the null finds cross. So my equilibria are, let's see, 0, 2, 2, 0, 0, 0, and whatever that point is right there, which I probably, so here's what we're really doing. And this is actually very similar to how we were finding and classifying the critical points of functions of two variables. Right? For finding the critical points for functions of two variables, we were setting the partial derivatives both equal to 0 and then finding all the simultaneous solutions. That's what we're doing here. If I look back to here, I'm finding the places where both of these are equal to 0 at the same time. 0, 0 is one of those points, right? If I plug in 0 for x and 0 for y, I definitely get that this is 0 and this is 0. And it might be helpful if I actually factor these. So let me factor in here so you can see it. Right, so if we plug in 0 for x and 0 for y, we definitely get a solution to both of these equaling 0. If I plug in 0 for x and 2 for y, well, if I plug in 2 for y, I get 2 times 2 minus 0. That's 2 times 0, which is 0. So 0, 2 is a critical point, or sorry, an equilibrium. And so is 2, 0. So I plug in 2 for x and 0 for y, I get a 2 here, but I get a 2 minus 0, which means that this part is 0. And then this part's also 0 because y is 0. And then the last point that I haven't found yet that I know is something like, I don't know, 2/3, 2/3, or I don't know, something where x and y are the same, is when these two lines cross, meaning it's where y equals 2 minus 2x and y equal to -1/2 x plus 1 cross. Plus 1? Yeah, plus 1. So if I set these equal to each other, I get 2 minus 2x equal to -1/2 x plus 1. Solving for x, let's say I'm going to add 2x here. So I'm going to get 3/2 x equal to subtract 1. I get 1. And then I really guessed, but I guessed right. 2/3 equals x. And then if I plug in for y, to find y, 2 minus 2 times 2/3 is 2 minus 4/3, which is also 2/3. So one of the nice things about graphing the null lines is the intersection of different types of null lines show us where we have equilibrium. So then we're going to do this thing, which is, I'll be really honest, I find this challenging to do. I always have to really think about what I'm doing when I do this. Where we're going to kind of say, we're gonna try and draw the direction field without actually just using p-plane. We'll also use p-plane in a second, but I always feel like I have to start with at least one point. So I'm gonna plug in, say, 1, 1, which I know is over here, right? So I hear my cat scratching. She really wants to come in and hang out with me. So if I plug in 1, 1 just for a second, here's what I get. If I plug in x equals 1 and y equals 1, I get dx dt equal to 1 times 2 minus 1 minus 2. Let's do 1 times 2 minus 1 minus 2, which is negative 1. And dy dt is probably going to be the same. I get 1 times 2 minus 1 minus 2, which is also negative 1. So that means at the point 1, 1, I'm going in the left direction and the down direction because dx dt is negative and dy dt is negative. So from over here, I'm going that way, towards that point. But more importantly, and gosh, I have to really, my brain has to make this. So here's what I know. I know that, how do I want to write this? Sorry, I like to kind of write like this. I know that the direction of travel in the x direction is negative, and the direction of travel in the y direction is negative. So I'm going left and down. And the thing is, that can't change until I cross one of my null lines. So this null line, where dx dt is equal to 0, once I cross this null line to be over here, the direction of travel in the x direction changes. Right? It was negative, here it's 0, and then it's going to be positive. So over here, I have what I like to write like this, a plus minus. Gosh, you guys, I'm sure you can't see that. Sorry. I'm trying to make that a little bigger. It's a plus minus, meaning my arrows are going right and down because dx dt is positive and dy dt is negative. So I have arrows doing, this sort of thing. Whereas on this side, my arrows are doing this sort of thing. And I'm bad at drawing these things. Like I'm trying to look here, like I'm always not good at getting the steepness right. And then on this line here, we know the arrows are going purely down. Right, because, well, they can't be going up. Like we're in a region where dy dt is negative, and they can't be going left or right because they're on an x null line. So basically, the null lines kind of separate which way things are going. So up here, my arrows are all going, this way, and maybe it's more like this, maybe it's more like this, but they're all going down to the left. And then when I cross this one, where dy dt is 0, so I'm going from dy dt being negative to 0 to dy dt being positive. So now everything's going to the left, but up. And then I'm crossing here an x null line. So instead of going to the left, now I'm going to be going to the right. Don't give my arrows too much credence. I'm looking at the actual picture of what this supposed to look like. I'm like, okay. And so, but we can kind of, the thing is here, you can kind of fill in what all these are. So like if you keep doing this, right, this is going to be plus, plus. Over here, again, I'm crossing a y null line, so the direction of the y thing changes. Here I'm crossing an x null line, so the direction of the x thing changes. Crossing a y null-cline, the y thing changes. Crossing a x null-cline, the x thing changes. Crossing a y null-cline, the y thing changes from positive to negative. So we got a couple sections here. Crossing this x null-cline, we're going to go from positive to positive. Crossing this y null-cline, we're positive negative. Here we're negative positive. So what this can kind of tell you, right, is what, and I'm not gonna lie. So let's look at the picture that our good friend Grant has drawn over here. Not that picture, not that. This picture here. So if we look at this, these are, so I should, I got my colors backwards from what he did, unfortunately. So my green null-clines or his red null-clines and vice versa. Oh, well, that happened. So what you can kind of see here, though, is right, like, oh, and I forgot to draw. That's what I meant to draw. Sorry. Well, let me stop sharing for just well, I can see. So I meant to draw the arrows on the actual null-cline. So let me go back for 1 second because that's something we should be able to do. So what I should have done, I said, okay, so once I know that, you know, on this y null-cline, that things are going to the right, because over here, we're like, I know that this has to be purely to the right. All right, those are the arrows that I actually need to be drawing. So as a reminder, all the y null-clines have purely horizontal arrows. All the x null-clines have purely vertical arrows. This one's going purely to the right. And then when I cross over to this other side of this x null-cline, I'm changing the direction. So now we're purely left. And when I cross over this x null-cline, we're purely right again. Crossing over this y null-cline doesn't change anything. So we're just purely right, purely right, purely right, purely right. Which should jive with the little notes over here, right? In this region here, the change in x is positive, which means we should be going to the right. This region here also the same. In this region here, the change in x is negative. So things seem to be matching up with what I've written. For this green null-cline, this vertical, well, we can see that we're going down here. It's always weird when you have a y null-cline, or sorry, x null-cline that's vertical, because then just your arrows are on the line. So here we're going down. We crossed one of the other null-clines, so we change direction. We're going up. We cross one of the other null-clines, so we change direction. We're going down. Okay, we're almost done. For this red null-cline here, they all should be horizontal. So over here, I don't know where to start. Over here, they're going to the left. How do I know that? Because of what I've done here, right? My change in x is negative. We cross the green null-cline, we're going to the right. We cross the green null-cline, we're going to the left. So we just keep doing that. And finally, this last one here should all be vertical. So here they should be going up till we cross one of the other null-clines and we change direction. And we cross this way again, we change direction. Okay, I know I said a lot. So here's what we can kind of see from this. If we look at all of our equilibrium points, we can try and kind of guess what happens. So look, if I start like here, I'm getting pushed to the right, and then I'm getting pushed down, and I'm getting pushed to the left, and then getting pushed back up. So it kind of looks like I'm spiraling around here. Same kind of thing is true over here. If I start here, I'm getting pushed up, but then left, but then down, but then right, and kind of like that. The origin definitely looks to be unstable. Right? It looks like everything is going away from the origin. It's probably an unstable node. It looks like a source. And this point here, I think, looks like a saddle, because although we're kind of like we can be pushing kind of towards it, we're also kind of pushing away from it. So let's say we're kind of doing that. So let's go back now. I might have said, I don't know. I might have said the wrong thing about that being a saddle. That might not be a saddle, really. Oh, no, I feel like it is, though. Let's take a look. So, if we look at this one, oh, sorry, I'm supposed to be sharing my screen with you guys. So, if we look, not at this one, if we look over this picture here, we can kind of see the things I'm saying, right? Like, at this point here, it definitely we can kind of see there's kind of a swirliness to the direction field. Same kind of thing here. There's definitely like there's the actual word that's not swirliness, whatever it is, a spiral. It's spiraling around there. Here it definitely has the look of a source, right? Everything is shooting out away from it. And here, I do think this point is probably a saddle, because we can see like from this direction and this direction, we're kind of pointing into it, but then we're kind of going away from it like that, right? We're going up like that and like that. So actually, ooh, let's put it into p-plane. Yeah, because then we can see what the paths of travel look like. So yeah, x times. I like p-plane a lot. I'm a fan. Because I like that you can click on it and see what kind of, because that's something, at least in the last 17C book people had to do, is you had to be like, okay, if you start with this initial condition, where are you going to end up? And for me, at least, it was hard to just like look at it and be like, well, I think I'm going to go this way. Whereas with this tool, we can actually get a much more accurate idea of what's actually going to happen. Okay, let's graph this thing. Cool. So let's see. Am I about the same? I could, let me change this. Let's make it so we match this real quick. So we're -1 to 3 and also -1 to 3. It's good to match. Let's do that. Okay, that looks a little. So here's our source, and we see that if we start anywhere here, right, we go out and then away. Interesting. So right, we're going. So it looks like we're kind of hitting this. Maybe I was too close to an eigenvector. So it looks like we're kind of going towards this, up towards this equilibrium point here, right? We're definitely ending at the equilibrium point 0, 2. What if we start somewhere like over here? Okay. So yeah, it looks like we're getting, a lot of them are shooting us to 0, 2. What if we start over here? Okay, then we swirl around to this way here. So yeah, cool. So it definitely looks like 0, I would say 0, 2 is probably some sort of spiral, right? It definitely looks like we're spiraling around to get there. Same thing for 2, 0, which isn't surprising because of the symmetry of our system. Cat. This is definitely a source, and I would have to say this definitely looks like a saddle, because it looks like right here, like I might have grabbed one of the, ooh, that's interesting. So we got diverted away from the saddle towards the source here, towards the spiral here, the stable spiral, I should say. But it looks like, right, it would be really hard to get to this point unless you happen to click right on whatever if there was an eigenvector, whatever that may be. Right, but it looks like most of the time we're getting bounced away from it. So, but it looks like there's not really, it looks like, okay, here are a couple places where you actually, so if we start over here, we start down here in the third quadrant, it looks like we are completely unstable, right? We don't get pushed. So this initial condition over here looks like we aren't going to end up at any of the equilibrium points. Whereas it looks like if you start in any of the other quadrants, you probably would. I want to do another example. So I guess we'll look at this example next time. And then we'll also talk about how, so you can totally look at the phase plane and kind of get an idea of if you have equilibria or not, or I mean, what kind of behavior you have around each of your equilibria. But there's actually a way using matrices, using a linearization of our differential equations, and then evaluating the matrix for that at each of our equilibrium points, to be able to then look at the eigenvalues and see the same sort of thing. Is it a source? Is it a sink? Is it a spiral? Whatever. So that's what we're doing. All right, so nothing. I was going to show you guys my cat, but she went away. So, oh well. Next time. She really wanted to come in here, but she left. What? Oh, where is she? She was scratching the door. Okay. We can meet everybody. Oh, you don't want to meet everybody now? It's my cat. One of my cats.
What's its name?
Sparky. Okay. She likes to sit in my lap, is what she really likes to do. So I'll let her do that in a minute. I'll try to get you guys' quizzes graded pretty soon, and thank you. She's an old lady, but she's a pretty great cat. And I think some of you guys have another midterm coming up in the not too distant future. Let me check real quick here. Let's see. Yeah, both Rodemacher and Carlson. I mean, it's still a ways away, so we won't worry too much about that, right? So, all right, that's all I got for you guys today. If there's something you feel like we're not talking about that you want to see, let me know, and I will try to make sure we talk about it on Friday. All right, that's all I got. Bye.
Thank you.
You're welcome. Good seeing you guys.